Well, how are you doing? This is going to be hopefully a quick video on uh, an 8 year thing that's going on, an 8 year challenge that keeps on being put into our faces from our opposition called the Polaris Challenge. It's such utter rubbish. I mean, we've told them time and time again, and we've shown them it's just perspective. And our opposition just haven't seemed to be able to grasp that. Now, hopefully, this video will put an end to all that nonsense. The reason this video is I'm making it now, I could have made it before, but the problem was is that it wasn't established up until recent times that the whole globe model, the radius for the globe, the diameter of the circumference, and all that's the globe is or that's built around the globe model, all of heliocentrism, that it all started with flat out elevation angles to Polaris. Because an elevation angle will not only give you, it won't be just the angle, right, to the celestial body. You will also have to correct to make that angle a right angle. And the baseline of that right angle is going to be horizontal. So when you sail away from Polaris, sail south towards the equator, Polaris will appear to drop in the sky. And every time you take an angle to Polaris, right, every time they took an angle to Polaris to find out this information, they had to correct the angle, right? Whether it was true sextant or whatever else they used, astrolabe or whatever, they had to correct the angle to bring it down to the surface of the water underneath the boat. That's the only way they could really figure this stuff out. They had to use a boat. They had to sail south. So consequently, those corrections meant that you needed a right angle at the GP of Polaris and underneath the water of the boat, and that meant that the baseline of that right angle was, because it always is and it was always going to be, a horizontal. So you have to use flat out horizontal distances to measure elevation angles. And that's where they built the globe model off. But that's I've covered that in a video recently. But the Polaris Challenge thing, right? I've seen some comments about that since I made the video about how the globe model is built off of a flat earth. So when someone asks for one of us, where is your flat earth model? We can just show them the globe, because that's the model that's built off of the flat earth. The flat earth is the reality. The globe is the model. You know, it's nonsense. But the globe was built off of flat earth elevation angles to Polaris. So I'm going to get stuck into this video and you'll understand, right, in a minute. This is about, right, first, what is the angular resolution of the human eye? About 1 arc minute, about 1 minute of a degree, right? The human eye has an angular resolution of about 1 arc minute, 0.02 degrees or 0.003 radians, right? Right, so it enables us to distinguish things that are 30 centimeters apart at a distance of 1 kilometer. That's pretty good, right? Very, very good, the human eye. So now I just want to go to here. How far past the equator can Polaris be seen? From more than 2 degrees south, you really can't see it except maybe from an airplane, right? So 2 degrees south of the equator, and you'll start losing Polaris, right? So they say from an airplane you will probably see it past 2 degrees south, but that's because you have a greater angle of view. That's what that is about. When you're close to the surface, which you will be, especially if you're in a boat. You're close to the water underneath you, so your view is very horizontal and limited. Whereas from an airplane, you don't have such a horizontal view. You have a horizontal view, but your view to the surface has an angle to the surface from your eye line, and you also have your horizontal straight out. So you're looking above the horizon at a distance, let's just say, right? But either way, right, from the surface, I can still see Polaris up to about 2 degrees. They say 1.5 or whatever, 2 degrees. I've seen, over the years, I've heard of mariners who supposedly said they saw it further, and people say that they see it regular and they're further than 2 degrees south. But I don't know about that. I'm not going to argue about it. It says here 2 degrees. I'll go with that for the moment, right? So this is astronomy.com, and this is Polaris visible from the southern hemisphere? Right. So I'm not going to read this top part because it's not important, right? It's just this bottom part that's important. Although Polaris is also known as the North Star, it doesn't lie precisely above Earth's North Pole. If it did, Polaris would have a declination of exactly 90 degrees. Now, I don't know about if that's true or not, but this is just what they're saying. Instead, our navigational beacon currently has a declination of 89.34 degrees. The difference 0.66 degrees would be Polaris's peak altitude if viewed from the equator, and the latitude south of the equator from which the star would scrape the horizon if Earth had no atmosphere, right? So what they're talking about there obviously is about celestial refraction. So if there was no air, right? Because if you're looking at Polaris from the equator, you're looking at it. If you're looking at Polaris from the equator, you're looking at it basically in your horizontal. So you're looking at it through a lot of density of air. So you're going to have it appear higher than it really is. And they say down here is like it adds, like if you under normal everyday what they call atmospheric conditions, it adds 0.57 of a degree to an object's altitude. So Polaris would barely show up at 1.23 degrees south latitude. But what they're not really saying is that it would be more than 0.66 standing at the equator, right? It would be higher than 0.66 degrees if you're standing at the equator. But the thing about it is that without the air, it would be 0.66 degrees, right? So how are they working this out? How did they know it would be 0.66? Well, the thing is this, right? Here is Polaris. Here's all these different angles to Polaris. The further someone is from the GP of Polaris, which will be here, the tighter the angle, the more shallow, I should say, the angle, right? The closer someone is, the wider the angle, right? So if someone is standing here and there's Polaris above them, right, then Polaris is whatever height above that person, right? And as that person moves away, Polaris appears to drop in the sky. So what's really happening is the distance between Polaris, let's say this is Polaris here, between Polaris, we'll call the lower limb of Polaris, right? And here is your equator. That has an angular, that's what I call angular free space, right? You can give it an angular size, basically, right? But it isn't anything, it's just empty free space, right? But as you move away, that free space, right, will not increase. As you get closer, it will increase in size. But as you move away from Polaris, that angular free space will decrease in size. So bit by bit by bit, that space between the bottom of Polaris and the horizon will decrease, and bit by bit by bit, it'll become smaller and smaller and smaller. And as it does, Polaris will also appear to drop, right? Because the space between the bottom of it and the horizon, that angular free space, is changing in angular size. It's getting smaller and smaller and smaller, right? So I just bring this back up and then this back up here, right? So let's go up a bit more, right? So this is the thing, right? This area here will get smaller as you move away, right? There's no way for that not to happen. And it's getting smaller because of its angular size is changing. So I just go here a second. Now, distance, 5,400 nautical miles. Size, I gave that angular free space 63 nautical miles, right? And when I calculated it, it came out as 0.66844 degrees. So at 63 nautical miles, now I don't know if Polaris is 63 nautical miles up in the sky. I don't know if it's 27 nautical miles up in the sky. I don't know what height it is. I don't know what it is. I don't know if it's a physical thing. I don't know what it is, right? But the angular free space, right, if I give it a 63 nautical mile height, right, that or size, the angular free space, which is here. If I give this purple rectangle here 63 nautical miles from here at the horizon to the base of Polaris, the lower limb they call it sometimes, up here, right? 63 nautical miles. At 54,000, at 5,400 nautical miles away, right, that's going to have an angular size of 0.66844 degrees. Absolutely matching what they say over here, right? And this is all using a flat plane. You have to use a flat plane to do it. There's no other way. So, so for years, like our opposition have said, this doesn't work on a flat plane and blah, blah, blah. The angles to Polaris don't work on a flat plane. Like angles to Polaris, how are you going to use an angle without a flat plane? You know, there's no thought ever went into it with these people. But here is evidence that, yes, at 63 nautical miles of angular free space between Polaris and the horizon, that area would be 0.66 degrees, 0.66844 degrees, right? Right, that's what you would, and that's exactly matching what they say. Polaris would be above the horizon if you were, you know, at the equator, which would be 5,400 nautical miles, right? So this totally matches what their claim is, and it can only happen on a flat plane. You can't. There is no such thing as an elevation angle on a globe Earth. It's completely impossible. So there you go. There is your absolute proof. Totally matching, right? At 63 nautical miles of angular free space. The thing about it is that I could make this smaller, 27 degrees, or 27 nautical miles, and it's 0.2 degrees. So maybe celestial navigation is actually, celestial refraction is actually making Polaris seem even higher in the sky than we know. Maybe that is going on with Polaris. And Polaris is not 63 nautical miles of free space high. It's actually 27 nautical miles of free space high. You know, whatever Polaris is, I don't know. But the thing is that you can change it, but at 63, it matches it. Now, I don't think there's 63 nautical miles of sky up there. I could be wrong. I reckon it'd be more closer to 27 or 36 of nautical miles of sky up there. But either way, it doesn't matter because 63 matches it perfect. Anything less than that will still match it. It'll just be a little less than that. The point is that this can only be done on a flat plane. This totally matches what astronomy.com are saying. You know, I don't see how there can be really much of an argument against this. You can't have an elevation angle without a flat plane, so that's the end of that. And we're able to absolutely match exactly what they say. You know, so this angular free space here, let's say it was 63 nautical miles high from the horizon here to the base of Polaris. Then as you move away, it gets smaller and smaller and smaller and smaller and smaller and smaller, and you end up at the equator, and Polaris is down there. You know what I mean? That's all that's happening. It's not really down there. It's still 63 nautical miles high, or 27 or 36, whatever nautical miles high. The point is that angular free space has changed in size, angular size. That's all that's after happening. I really don't know. I really don't want to hear ever again about this Polaris challenge nonsense, because the Polaris angles, the elevation angles to Polaris is what the globe Earth is built on. That's why the radius, the two radii have to be exactly what they are. They can't not be anything else, and the average radius has to be exactly what it is. The globe Earth can never be any bigger or smaller than it is. It has to be exactly that. For the elevation angles to Polaris to be backworked into the center of a globe. But the elevation angles to Polaris are all taken from the surface, and they all require a flat surface. So when someone asks, if you're a flat earther and someone asks you, where is your flat earth model? You show them the globe, because the globe is the flat earth model. The flat earth is the reality. The globe is the model. Thank you.